Hello and welcome to my second video on MCTS, Monte Carlo tree search. The link to the last one you can see above. The last one came with a catalog of theoretical errors, so this video is about fixing some of those and having some fun with animations. So let's start with the same problem as in the last video. A simple TSP or traveling salesman problem, where there is this state and the aim is to go from the bottom left, the blue node, then visit all the black nodes in some order and end at the top right, red node, and to do all this with the least amount of distance traveled. We're standing here now, and first step is to take a look at all the possible moves from the starting position. This is called expansion, and it's one of 4 key components in MCTS, the others being selection, simulation, and backup. Selection precedes expansion, but in this first step there are no nodes to select from, so we do expansion instead. It basically means the creation of one or more nodes. N stands for visited counts and V stands for value, and here they're all initialized to 0. There are lots of different ways to implement this, and there are some heated debates about how to do it the best way. But in this particular implementation, all the possible child nodes are always expanded. And after that is done, one of them is picked randomly, and then a simulation is launched from that node in the following way. The simulation follows a so-called simulation policy, and here it is uniform random, so next moves are selected randomly. One key difference between MCTS and a more standard Monte Carlo algorithm is, as you can note, there are no visited counts or values for the simulated nodes. We really don't care about them. They're said to be out of tree, as opposed to the nodes initialized above, which are said to be in tree. And the reason for doing this is to reduce memory usage. When the simulation reaches the bottom, the total distance traveled or value can be computed. And now the next step, backup, has already started. The simulation path is removed because we don't need it anymore, and we start with the node from which the simulation was launched and update the value. And we would then send this value upstream to the parent of this node, but in the first iteration there's no relevant parent to send it to because the first move is done on this level. Also the visited count is incremented. And now we're done with the first iteration, and at this stage we return to the root. In the second iteration, there are now child nodes to select from. And selection is always triggered when there is at least one child node available. And here's the cool part. Selection is not random. It does not follow the same simulation policy as was done in the simulation step, but rather follows the so-called tree policy, which uses the action selection equation. And I won't go into detail about this equation, but basically it makes use of these visited counts and values. Q here is what's known as an action value, and so I could have put Q here, but Q is normally in the range 0 to 1, and what I show here is distance traveled, and it overflows the boundary here a bit, sorry for that. It should say 122.0, but they are proportional. Q and V are proportional. So which node is going to be selected? So it makes sense to not select this node because it has already been updated once, and this equation makes sure that this intuition is followed. So this node is selected. Selection always continues until a leaf is reached, so this was a leaf, and at that point expansion is triggered. You could ask why a simulation or a rollout, as it's also called, was not launched from this node, but that depends on the implementation. If function approximation is used like deep learning, it makes perfect sense to generate a value estimate whenever a node is generated. But here no function approximation is used, so it doesn't really matter. And then a simulation is launched from one of the nodes as before and backed up as far as it can get. I will now fast forward a bit to the next interesting thing that happens. You can see in this animation that positions of the nodes on the drawing board are adjusted whenever more nodes are added at the same depth. So now all possible start moves have the same visited count of 1, and therefore the next selection is a mix between a random variable, which ensures that exploration continues, and the value. And here we're trying to minimize distance, so a low v leads to a high q. That's how they are proportional. Whenever there's a backup from, say, this node to this node, and there is a previous value already waiting here, it is updated as an incremental mean. This is now run for 50 iterations, and sorry for bringing this thing up again, but this c here, constant, is one that is set between 0 and 1, and it can be used to manually override the level of exploration. So everything on the right hand side here is exploration. It's known as UCT, or upper confidence tree. And the lower this c is, the less exploration there is. In this run, it was 0.2, and now I'll show what the search would look like if it were 1, and therefore exploring much more. We can see that the visited counts are much more even among the first moves in this case. And this may seem a bit counterintuitive, because isn't more exploration supposed to make things go a bit crazier? But here, this looks like a much more regularized tree than the other more asymmetrical one. But everything is as it should be. This tree is a result of higher bias, with the first node there being more exploited, whereas this tree is a result of higher variance, or less exploitation and more exploration among the possible moves. This is an animation where MCTS works exactly the same way as before, but without showing any states, only the connection lines between the nodes as they grow, and this is on a larger problem. So the reference is the real example on the left there, and I didn't quite get there. But it was fun to try to get the animation to look like it. The analogy of MCTS simulating a tree trying to figure out where to grow a root branch next probably doesn't reflect reality at all. But it is called tree search after all.